Hello everyone. In this video I want to talk about convex order when you are looking at two risks at the same time. So assume we have the following situation. We have an insurance company who has a business in two different regions. For example, he has a business in Europe and the loss that he will get because he is doing business in Europe is denoted by X. And the same insurance company also has a branch in North America, and the loss in North America is, for example, denoted by Y. Then the total loss of this insurance company is the loss that comes from Europe and the loss that comes from North America. So it means that we have to add the two losses. So the total loss is X plus Y. We will use the random variable S to denote the total loss that the insurance company is facing. So S is X plus Y. And we know that if we are looking at different random variables, then the distribution of S is a combination of individual information, meaning the distribution of X and the distribution of Y, and the dependence information. If the random variables X and Y are very positive, very negative dependent, or independent, then this will change the distribution of S. So in order to know the distribution function of S, we need the following. We need the marginal distributions, which we denote by Fx and Fy, and we need the dependence information, or as we have shown in chapter 3, the copula that couples the marginal distributions to get the joint CDF. For this exercise, we assume that the marginal distributions are known. So we assume very specific and very simple dynamics for our marginal risk. So the random variable X can take a value 0 and it can take a value 100 with equal probability. So it means that for X you either have no loss at all, you get 0, or you have a loss of 100. And we assume that the distribution of Y is the same. So the probability that Y is equal to 0, it's equal to the probability that Y is equal to 100, and both probabilities are 1 over 2. So we know exactly what the marginal distributions are. But in order to determine the distribution of the sum of X plus Y, which we denoted by S, we need to make an assumption on the dependence information. So assume first that the random variables X and Y are independent. In this case, we need to introduce a new random vector for our two losses, the random vector that uses the marginal distribution of X and Y that we have here, but puts a independence copula on top of these marginals. So we denote by X independent, Y independent, this random vector, it's the so it means that our real situation is described by the random vector X plus Y. The independent counterpart, X independent, Y independent, is a random vector having the same marginal distributions as the random variable X plus Y. So it means that X independent has the same distribution as X. Y independent has the same distribution as our original random variable Y. But for the dependent structure, we have that X and Y are now independent. So it's important we introduce a new random vector, X independent, Y independent, having the same marginals but a different dependent structure. Now we assume that everything is independent. Because now we determined the marginal distributions and we determined the copula, dependence structure, now we can derive the exact distribution of our random variable s. So now we have determined the marginals and the dependent structure of our random vector x independent, y independent. So now our goal is to derive the upper tail transform of the sum x independent plus y independent, which we denote by s independent. All right, because the upper tail transform will tell you something on the extreme positive losses, and that's where, because we are looking at loss random variables, that's where the risk is. Alright, so before we can determine the distribution function of the sum, let's first do the joint probability. So for example, derive the probability that both x and y are taking a value 0. Because we have an independent vector, this is just the probability that x is 0 times the probability that y is 0. We have here x and y independent, but because x and y independent have the same distribution x and y, this is just the probability that x is 0 and the probability that y is 0. And for x and y, we know these probabilities, it's 1 over 2, and again 1 over 2, so this probability is 1 over 4. And you can repeat the same technique to derive the probability that x is 0, y is 100. Also, this probability is 1 over 4. The probability that x is 100 and y is 0. Also, this probability is 1 over 4. And lastly, the probability that both risks are taking a value 100. Also, this probability is 1 over 4. That's something you directly find if you apply that x and y independent are independent. Let's then have a look at the sum s independent, which is x independent plus y independent. And we want to have the distribution function of the random variable s independent. So let's start with the probability function. For example, what's the probability that s is equal to 0? Because x and y are taking value 0 or 100, s can only be 0 if we have that x is 0 and y is 0, which is, that's what we derived on the previous slide, is equal to 1 over 4. If you now derive the probability that s is equal to 100, there are two possible situations where s can be 100. We have x is 100 and y is 0, or we have x is 0 and y is 100. And from the previous slide, we know that both probabilities are equal to 1 over 4, and 1 over 4 plus 1 over 4 is 1 over 2. And you can also derive in the same way that the probability that s is equal to 200 is equal to 1 over 4, because it's the probability that x and y are both equal to 100. If we then use that the CDF f as independent in some variable x is the probability that s is small equal than x, then you directly find that this CDF is given by the following expression. It's equal to 0 if x is smaller than 0, because x and y are both 0 or 100, so for your sum you never can get anything negative. If x is in the interval 0, 100, the sum s can never take a value which is strictly larger than 0 and strictly smaller than 100. If you want to be in the interval 0, 100, where 0 is included but 100 not, it is the situation where your sum is equal to 0, and this occurs with probability 1 over 4. If you have to be in interval 100, 200, this only happens when both x and y are equal to 100, so this is 1 over 2 plus 1 over 4. And finally, x larger than 200, it's 1 over 2 plus 1 over 4 plus 1 over 4. And then you find that this is equal to 0 if x is smaller than 0. It's equal to 1 over 4 if x is between 0 and 100. It's 3 over 4 if you are in between 100 and 200. And finally, it jumps to 1 in 200. And this is your CDF. We now have the CDF. We can then use the CDF to determine the stop-loss premium or the upper tail transform, this expectation as minus k plus, which is equal to an integral from k to plus infinity 1 minus the CDF f as independent x dx. Alright, so in order to calculate this integral, we do different cases. So first assume that k is larger than 200. Then since the sum s is always smaller or equal than 200, the sum s can never exceed 200, we directly find that the expectation s minus k plus is equal to 0. Okay, that's case 1. Then assume that k is in the interval 100-200. Then we have that this stop-loss premium, you can write it as an integral k 201 minus f s x dx. But we know from our previous slide that in this interval, the CDF f as x is a constant and is always equal to 3 over 4. So this integral becomes an integral from k to 200. So the upper bound is 200 because we cannot exceed 200. So we can stop our integration at 200 and not at plus infinity. So we have 1 minus 3 over 4, which is 1 over 4 dx, which gives you 1 over 4 200 minus k. Finally, assume that k is in 0, 100 in this interval. In this case, our stop-loss premium is equal to, we integrate from k to 200, 1 minus the CDF. But now we split our integral. We first go from k to 100 because we know that k is smaller than 100. 1 minus the CDF. And then we go from 100 to 200, 1 minus the CDF. Because now my CDF is constant in both intervals. Here the CDF is equal to 1 over 4, and here the CDF is equal to 3 over 4, which means that you get 1 minus 1 over 4, 100 minus k, plus 200 minus 100, 1 over 4, which is of course 25. So you find here 3 over 4, 100 minus k, plus 25. And then we find that the stop-loss premium is given by the following expressions. If you are smaller than 0, it's of course 100 minus k. If you are between 0 and 100, it's 25 plus 100 minus k times 3 over 4. If you are in the interval 100-200, it's equal to 200 minus k divided by 4. And if you exceed 200, it's equal to 0. If we draw this upper tail transform, we have the following plot. In k is equal to 100, the stop-loss premium, because s is positive, the stop-loss premium is equal to the expectation, it's equal to 100. If k is equal to 100, the stop-loss premium is equal to 25. And if k is equal to 200, the stop-loss premium is equal to 0. So the curve is this convex piecewise linear curve. This is a stop-loss premium expectation as bar independent minus k plus. On the previous slides, we considered the independent counterpart of the random vector xy. So we considered a random vector having the same marginal distributions as xy but an independent copula. Let's now look at the random vector xm, ym, which is the mutual exclusive counterpart of our random vector xy. So it means that xm has the same distribution, this two-point distribution x, and ym has the same distribution as our original marginal variable y. However, in the mutual exclusive counterpart, we have that xm and ym are mutual exclusive. What does that mean? Mutual exclusivity, it means that the probability that xm and ym are strictly positive at the same time, that probability is 0. In our particular situation where xm and ym are now having a distribution that can take value 0 or 100, it means that mutual exclusivity means xm equal to 100, ym equals 100, that occurs with probability 0. So if you now use that xm has the same distribution than x, that means that the probability that xm is equal to 100 is equal to the probability that x is equal to 100. They have the same distribution, and that should have probability 1 over 2. However, mutual exclusivity gives the following result. The probability xm equal to 100, I can write it as when is xm equal to 100? It's the case when xm is 100 and ym is 0. Or it happens in the situation where xm is 100 and ym is 100. Alright? But this has probability 0. From equality in distribution between xm and ym, we know that this has probability 1 over 2. So our conclusion is that this probability here is equal to 1 over 2. So we find that this probability is equal to 1 over 2. We also had, that was mutual exclusivity, that the probability that xm is equal to 100 and ym is equal to 100, this probability is equal to 0. And using the same argument as we did on the previous slide, but now with ym equal in distribution to y, we also find that the probability that xm is equal to 0 and ym is equal to 100, this probability is equal to 1 over 2. And then you see that you have an event with 1 over 2, another event with 1 over 2, so then you also find that the probability that xm is equal to 0 and ym is equal to 0, this probability is equal to 0. So if you then look at the random variable Sm, which is the random variable, it's your sum when your random variables are mutually exclusive, this Sm random variable is equal to xm plus ym, but we have that under mutual exclusivity, xm equal to 0 means ym equal to 100, and xm equal to 100 means ym equal to 0. So that sum, if you add these two, you always get 100. So the probability that our mutual exclusive sum Sm is equal to 100, this probability is equal to 1. And then we have a look at the expectation Sm minus k plus, the upper tail transform. Well, this upper tail transform, if k is smaller than 100, this will give you 100 minus k. If k is larger than 100, this will give you 0 because Sm can never exceed 100. We have here the plot that we made before with the upper tail transform of our independent sum as independent, let's now add the upper tail transform of our mutual exclusive sum. For the mutual exclusive stop-loss premium, we know that in k equal to 100, we get the value of 0. K equal to 0, your stop-loss premium is equal to your expectation is equal to 100. So the stop-loss curve, the upper tail transform of the mutual exclusive sum, is given by this curve. It's going to 0 from 0 to 100, and then it is always equal to 0. So this is the expectation Sm minus k plus. And then we directly find that the expectation of Sm minus k plus is smaller or equal than the expectation of the independent sum. We also know that because Sm and S independent are both sums of random variables with the same marginals, the expectation of Sm is equal to the expectation of S independent. If you combine these two relations, you conclude that Sm is smaller in the convex order than S independent. What does this mean? It means that if you are facing two risks, X and Y, then you prefer that these risks are connected in a mutually exclusive way over an independent way. If the risks are independent, your risk of your total loss S is more dangerous than when they are mutually exclusive. Why is that? Because if they are mutually exclusive, they are, in this particular situation, they are always compensating each other. What is your risk? X and Y. X can take a value 100 or 0, the same for Y. So if X is equal to 100, this is the bad situation. X equal to 100 means that you get a large loss for your portfolio X, same for Y. So what is the worst case situation that can happen when you have two of these risks? The worst case situation is when X and Y are both taking the value of 100. You want to avoid that. In the independent case, this happens with probability 1 over 4. It's as likely as when you are in the other situations. But in the mutually exclusive way, this has probability 0. There is no way that you can get X and Y at the same time equal to 100. So you're guaranteed that either you are in the bad situation for X, but that will be compensated by the good scenario Y equal to 0, or it's the other way around, Y is in the bad scenario, but then X is in the good scenario. So you prefer mutual exclusivity over independence because mutual exclusivity gives you compensation between your risks, or we also call that diversification.